In this video, we are going to continue our conversation about the topic of systems, and this time we're going to look at systems of 3 linear equations and 3 variables. I am going to have 2 videos on this topic, so this is the first of the 2. With 3x3 systems, as I will refer to them, there is more than one way to approach them. The process that we are going to be employing is going to be centered around the idea of putting the system into triangular form. When I say triangular form, I mean a form like this one. You will notice that the variables are lined up. X's are over X's, Y's are over Y's, Z's are over Z's, and the shape of the equations kind of makes a triangle. So it's very, very visual, like so. And what you can see in the triangular form, the first equation has all 3 of the unknowns still present. The second equation only has Y and Z, and the third equation only has Z. So I wanted to make sure that our first equation was already given to us in triangular form so that we could go ahead and see how do you find the solution once you have triangular form. So the process of finding the solution once you've got your system in triangular form is called back substitution. And when I say called, this is the terminology that your textbook uses. This isn't official terminology, but it is perfectly descriptive. So the way that back substitution works is, and again, it's handy to number your equations. We look at the third equation, and the third equation tells us z is equal to -2. Now that we know z, we're going to take that and we're going to plug it into the second equation to solve for y. At that point, we will know both y and z, and we will plug that into the first equation to also get x. So let's do it. Looking at equation 2, plugging the third equation into the second equation, we have y minus -2 is equal to 3. So I'm plugging -2 in for z. So that means y plus 2 is equal to 3. So y is equal to 1. So I have now y is 1, z is -2. And I'm going to take that and plug it into the first equation to get the value of x. So for the first equation, I have x minus 3y, but y is 1, okay, plus z, but z is -2, and all of that together is supposed to be 0, so that'll be x minus 3 minus 2 is 0, so x minus 5 is 0, so x is equal to 5. So now I have values for all 3 of my variables, and I write my solution much the same way that I wrote my solution for 2x2 systems as an ordered pair. Here it'll be an ordered triple. So the value of x, the value of y, and the value of z. Very briefly, in our first video, we looked at the graphical representation of the system. The graphs were lines, and we were looking for the intersection of 2 lines. Here we have a third variable in the mix, which makes the graphing more beautiful and also more complex. With a third variable, in order to graph, we would need a third axis, which means we would also have a third dimension. So the graphical representation of 3x3 systems is 3-dimensional. Each of these represents a plane So like a piece of paper you can think of as a plane. And so what you are looking at here graphically is the intersection of three planes. So Desmos does not graph in 3 dimensions by default. So it's a little bit more difficult to see this represented graphically. And so that's not going to be a big focus for us. But if that's something that you're curious about, I'm happy to explore it further with you in office hours. Okay. So for our second example, I wanted to look at a system that isn't given to us in standard form, or I should say, excuse me, in triangle form, and I want to put it into triangle form. To do this, we should have some ground rules, things that are permissible when it comes to the process of putting a system into triangle form. So I wrote those out, and I saved them so that I could enter them at the correct moment. So here are the permissible things to do. Add a non-zero multiple of one equation to another. So that's very similar to what we did with the elimination method with 2x2 systems. Multiply an equation by a non-zero constant. So these two kind of go together. And interestingly, interchange the positions of 2 equations. So you'll see how this third one can be really handy in the next example that we do. When you are going through this process of putting a system into triangular form, it is especially important to number the systems so that you can refer to them and so you can keep really clear what you're doing at any given step. So remember, triangle form leaves all 3 variables in the first equation, eliminates the x out of the second equation, and eliminates both x and y out of the third equation. Now, you might be looking at this and thinking, well, x is by itself in the second equation. That's going to make it easier to use the second equation to eliminate x out of the other 2. That's going to generally be the case. When you have a singleton variable, that's going to, especially a singleton x, that's going to make us want to use it as our top equation. So that's going to be my first step. I'm going to rewrite this system with the first and the second equation flip-flopped. So I'm going to put the second equation up top, then the first and the third. Notice that that is one of the 3 permissible operations. Okay, so here we go. I'm just going to rewrite it really quickly. Okay, there it is. Here is my first equation, rewritten but now in the second position. And then I've left my third equation alone. Oops. It's important to recopy it correctly, huh? Minus y plus z equals 1. Now remember, what I want to do now is I want to eliminate, in fact, let me write it this way. I want to eliminate x from the second equation. Now look, I have 2x as my x term in this equation and x as my x term in the one that's up top. So what I'm going to do is I'm going to take the second equation and leave it and add it to the first equation times -2. So actually I'm going to write it this way. I'm going to take the second equation and I'm going to add it to the first equation times -2. So I have, notice I'm not doing anything with the third equation here. X plus 2y minus 3z equals -4. That's my second equation. And then I have I misspoke. I'm taking the second equation times -2, and I'm adding it to the first equation. There we go. So that gets me -2x minus 4y plus 6z is equal to +8. And then the first equation is 2x plus 4y minus z is equal to 2. Now watch what happens when I add these. Both the x and the y are eliminated. So I have 5z is equal to 10, which I can divide both sides by 5 real quick to give me z equals 2. So in fact, I overshot. I meant to just eliminate x, but I eliminated both x and y. That will happen sometimes. So what I'm going to do now is, since I only want z by itself in the last equation, I'm going to once again interchange the positions of now the equation that was in the middle and the equation that was on the bottom, leaving me with x plus 2y minus 3z is equal to -4. That's my original second equation. Okay. Next, I'm going to write 3x minus y plus z is equal to 1. So I've moved my third equation into the second position. And finally, I'm going to write z equals 2, which is kind of this current version of my original first equation, in the last position. So I'm really close to my final form here, my triangle form. All that I have left to do is eliminate y, or rather x, from this equation. So I'm going to go ahead and copy what we're doing here so that I can move it to a fresh page. Okay. So since I'm aiming to eliminate x from this middle equation, I'm going to take my top equation, which is my second equation. I'm going to multiply it by -3, and I'm going to add that to the middle equation there, which is my original third. So I have -3x minus 6y plus 9z is equal to 12. And 3x minus y plus z is equal to 1. And sure enough, when I add these, the x's eliminate, and I'm left with -7y plus 10z is equal to 13. I've got my triangle form now. So I'm going to do this. I'm going to say original system, and we're going to put our original system here. And then down below, we'll look at the triangle form. Here. So for the original system, we'll copy it over from this page. So there it is. And then here is the triangle form. x plus 2y minus 3z is equal to negative 4. Negative 7y plus 10z is equal to 13. And z is equal to 2. So finally, just over here in the corner, we're going to find the solution using back substitution. So we already know that z is equal to 2. So we're going to plug that into the second equation here. So that leaves us with negative 7y plus 10 times 2 is equal to 13. So negative 7y plus 20 is equal to 13. Subtract 20 from both sides and you get, oh, negative 7y is equal to negative 7 and y is equal to 1. So now we have both x and y. I'm sorry, both z and y. And finally, we're going to take the values of z and y that we have now and plug them into the first equation to solve for x. So we have x plus 2 times 1 minus 3 times 2 is equal to negative 4. So that's x plus 2 minus 6 is equal to negative 4. So x minus 4 is equal to negative 4. We'll add 4 to both sides, and we'll get that x is 0. So the solution to this system, which we always want to take that moment at the end to write the solution as an ordered triple, is 0, 1, 2. What I am not going to do here that I highly encourage you to do, and this is a great last step, take this ordered triple 0, 1, 2 and make sure that it satisfies all 3 equations. In fact, I said I wasn't going to do it, but let's do it together. So let's get a nice green color going here. So we're going to check here. So bated breath. So first equation, 2 times 0 plus 4 times 1 minus 2. So I'm hoping that's 2. And sure enough, 2 times 0 is 0, plus 4 is 4, minus 2 is 2. Check. Not enough. We can't stop here. We have to check all 3. Next equation, 0 plus 2 times 1 minus 3 times 2. That should be negative 4, and it is. 2 times 1 is 2, minus 6 is negative 4. Check. And we still have to check that last one. 3 times 0 minus 1 plus 2. That should be 1, and it is. 3 times 0 is 0, minus 1 is negative 1, plus 2 is 1. Because putting a system in triangle form can be a bit of a journey, as it turned out to be in this case, it's really easy to lose something along the way. So taking that moment to actually make sure that the solution that you found satisfies the original system can be a really good way to ground yourself and to be confident, yep, I solved this system correctly. So I'm going to make a quick video after this one, just doing one other example, just because the process of putting a system into triangle form can be a little bit overwhelming and it takes some practice and takes some getting used to. But we'll conclude this video here. Stay tuned for the next video with some examples.